The last thing we want to look at here is angular momentum. And by now you might have sensed a pattern. This works very similarly to linear momentum. But there's one key difference, and that is that the vectors point perpendicular sorry, that's not what it is. The key difference that we will see here, sorry, I don't know why I was thinking along those lines. The key difference is moment of inertia changes much more easily than mass. So when we're looking at momentum, we typically looked at any changes in momentum were due to changes in velocity, because it's very hard to change the mass of something. But with angular momentum, like that classic example of an ice skater, right? If they're skating with their arms out, and then they bring their arms in, they've changed their they've changed their moment of inertia. If angular momentum is going to need to be conserved, if moment of inertia goes down, angular velocity needs to go up. And so we have here L is equal to I omega, where L is angular momentum. So again, if you reduced your moment of inertia, then your omega would have to go up. Conversely, if you increased your moment of inertia, then your omega would have to come down. And so that's the key difference with angular momentum, is we'll often look at both of these quantities changing, or both of these quantities can change, whereas we're kind of used to with momentum, it was really just the velocity changing. So back to that classic example, suppose an ice skater is spinning at 8.8 revolutions per second with her arms extended. She has a moment of inertia of 2.34 kilogram meters squared, and with her arms extended, and if she brings them in, it goes down to 0.363 kilogram meters squared. And these are assuming that she's about 60 kilograms. What is the angular velocity in revolutions per second after she pulls in her arms? Well, we know that angular momentum has to be conserved because momentum had to be conserved. So L initial has to equal L final. So in other words, I initial times omega initial has to equal I final times omega final. In other words, if we want to find omega final, the initial moment of inertia divided by the final moment of inertia times the initial angular momentum, times the initial angular velocity has to equal the final angular velocity. And so this will be 2.34 kilograms meters squared divided by 0.363 kilograms meters squared times omega, which was 0.800 revolutions per second. Okay, now technically this should be in radians per second, but because of the way this equation works out, and we're just looking at the ratios of these, we can leave this as revolutions per second, and our answer will give us the proper units. If you wanted to write it as radians per second, that would work. You would just get, it would work, you would just have radians per second as your answer. So if we work this all out, just so I can do the next part fairly easily, let me get out my calculator. 2.34 divided by 0.363 times 0.8 is going to equal 5.157 revolutions per second. So much faster, you can see, going from less than 1 to 5 revolutions in a second. For part B, what is her rotational kinetic energy before and after she does this? So again, comparing it to the 0, or from comparing it to not spinning at all is what we're really asking here. So I'm just going to shortcut and write 1/2 I omega naught squared as the initial, and the KE final will be 1/2 I omega squared. Now this is the case where I do need to now convert these from revolutions per second to radians per second. But luckily we've already done that kind of idea before, so 1 revolution is 2 pi radians. And so we can just use that to switch over. So this will be 1/2 I initial, which is 2.34 kilogram meters squared, times omega squared, which is 0.800 revolutions per second, times 2 pi radians per revolution. Square that, and then here we're going to get 1/2 0.363 kilogram meters squared times 5.157 revolutions per second times 2 pi radians per revolution squared. And let's run these numbers just so you've got them. So 0.5 times 2.34 times 0.8 times 2 pi to the second. I believe that gives us 29.56. So let's call it 29.6 joules. Double check that, did that real quick, so it's entirely possible I made a mistake. And then when we come to the second, we have 0.5 and 0.363 times 5.157. We've got 190.6 joules. And this is, again, similar to what we had said before, we don't necessarily expect kinetic energy to be conserved because momentum is what we do need to look at conserving. So the kinetic energy, the rotational kinetic energy, can increase. She's spinning faster, and faster spinning matters more than greater moment of inertia. So that'll wrap up kind of all the initial notes here. What we'll spend over the next couple weeks is getting into the details and kind of getting comfortable with all of these concepts. But for now, you've got the rough idea of all of them. Let me know if you have any questions about them.